Hello. Last time we looked about how we could optimize the code for better performance of the rotary knob, even at high frequencies. But we also looked at how to write the display, and we saw that several techniques were faster than others. And I showed you an optimization technique that it's not very accurate, but it gives you, if it performs well at a slow speed, then okay, then you know it's fast or faster. But there's another way. We can use the timer. So we can then set the timer to 0 and then call the function, and then when the function returns, we store the timer 0 number. And then, as you can see down here, we paint that on the screen with the same function though, but that doesn't matter. So what happens down here is the same as before, almost. So something come to my attention. The Highlander, you should check out his videos too, because he does coding himself. So on 8-bit micros, so that's very interesting. So if you like that, go out and check his channel. That was really great. So thank you very much. He talked about how fast the division is in CPU, so in machine code, and yes, I have checked this before, and division by 10 or by any number is performed with one of the fastest routines. We can have a look at that in assembler actually. We can try and see here what numbers we get. So the first thing I want to check is this one, this new one, into deck digit, and that's the way that it's working is that you have a modulo 10 operator. The modulo 10 means that the number is then the first digit, so you get the first digit in that number. Let me write an example. So 1 mod 10 equals 1, and 11 mod 10 equals 1, 21 equals 1, 221 mod 10 is also equals 1. So you see, it's the first number. Another example of modulo is the 12-hour clock, or 24-hour clock for that matter. So if you say it's 9 o'clock in the evening, and you say, okay, I'll be home 4 hours later, so you add 4 to that, it's 13 mod 12. And we know that if we leave the house at 9 and come 4 hours later, then it's 10, 11, 12, or 0, and then 1. So we know that's 1 o'clock. So it's the same way that it works for mod 10 also. However, we can't just pick out a number when the value looks like this, because we are going from one number system to another. So therefore we can't do that. So therefore we need another technique. I have looked at the listing. So sorry, I just had to compile it first. So like this, and now here. So as you can see, it uses division, and it uses 8 by 8. That means 8-bit division. So you can see when I do the modulo up here, we get division, and then when I do divide by 10, we also do division, of course. So it's done once, I think. So see, here it is, and you can see that it's using this moving. I think this is for moving bits, bit shifting. I'm sorry to say this, but I don't know this method, and it's not very long, as you can see, but it does have some repetition here. So if you single step it, you will see that it jumps 10 steps back, and it repeats that, because you know, when you multiply numbers you have to repeat stuff, you know, so for every digit. And in binary, I'm not sure. So, but I have read somewhere that this is one of the fastest way of doing it. So I'm confident that this one is fast. Okay. So let's have a try then. See how fast this one is. So you have a compile it, and you can see the number 13. 113. Here you can see the timer is running with a prescale of 4, and that means that it's the reason I had to prescale it was because it takes so long, so this timer will wrap around before yeah, it will wrap around. So divide it by 4, so the timer runs 4 times slower than the CPU instructions. So that's 452 instructions. But for now I'm writing it down and I say 113 times 4. I don't bother time by 4. So yeah, so let's try the next one. Oh wait, let's try and single step it. So, but single stepping 452, just to give you an example, let's do something more simpler. Let's take division by 10. So first, let's see how fast that is. And also I made sure that the compiler isn't optimizing away. So it actually is dividing by 111 in runtime and not at compile time, because that's a big difference. So of course. So it's 26, and that's what I have written down. You see, this is 26 times 4, so it's pretty fast. So maybe you should single step it, and then we have to go into the debugger to do that. So let's do that. You have to edit the project. You have to go for ICD debug, and ICD stands for in-circuit debugger. So that basically sets the microcontroller into a mode such that you can single step the clock, or the instruction clock though, so it's faster. Watch these LEDs here that I'm pointing, this long row to the right. What the fuck? I'll be right back. Okay, here's our fault, so let's remove that for now. It seems that it doesn't like to change these registers while in this mode. Down here. So now watch this row here, the one to this red LEDs. You see that? Something changed here. We can't see anything on the output yet, or on the display yet, because when data is put on that port D, then it's ready to be displayed, because now all the digits have that same data. But then you have to select which one is going to lit up, because they are multiplexed. So check it out. So let's move it. So now we put a value into port A, and you can see this light turned on to the very left there. I think yes, you can see it, and of course this one's on. So, and we can jump. Nothing happens. Oh, there you go. 0. So looks like the value is 0 every time. We are reading out the timer, and now the timer is not working in debug mode. So, well, but I wanted to show you single stepping, so let's do that for this function. So here we go. Let's jump here. And now the thing with this debugger is that when you step into something like this, for some reason I get into the assembly, and that's great. So you can see how that works. So now we are in division 8x8 unsigned. I think that's what it uses. So let's see. Let's count them. So 1, 2, 3, 4, 5, 6. '78, '79, '80, '81, '82, '83. So it took 83 clock cycles, and didn't we measure before 26? The 26 by 4 is 104. There's definitely something missing here. Those cancel. Let's run this code. Let's see what number we get. This shall get 26. There we go, 26. So there you can see. So let's try this function. It's not exactly the same. I have made it into a 8-bit function, so it takes an 8-bit number and then it converts it. So, but the other one could take a 16-bit number. So here I must be careful though, because this can be done in compile time, but 27 is not, it's not at compile time. I checked it before, but because it's at compile time we get a very low number there, so no. Let's try the modulo. So it's about the same, and the reason for that is because we, as we saw in the earlier, that when you do a modulo, it basically calls division by 10, so no problems. And here I have a mystery function that I made. Actually I made 3. This is a technique called, well, it's not a technique, but it's something I looked about. You can add a binary coded decimal together. So that's a little bit faster actually. So yeah, these small changes means a lot when those values are small, but like 113 and 114 isn't that much big of a difference. So this is the conversion with using mod 10. So I'm still dividing by 10. So I get that slow division, but I'm using my function mod 10. And it's a bit cryptical to see the least, but it's really fast. So you can see it's 89, so it actually helps. It helps. It's 89 contrary to 113, and the only difference with these, yeah, the only difference here, as you can see, this is the one that uses modulo and division from the compiler. So, and you can see I'm doing the same here, except I have my own modulo operator. Alright, so it's creeping down. 85, so it actually is worse. Yes, this is not what I was going to optimize, but I thought it was interesting to see. And also, if there's another way of making this division faster, then you can, if you can get that number further down. 10 modulo operator took 27, but after this technique we got down to 11, so I think that's pretty cool actually. So but the coolest thing of all here is this 12 times 4 cycles 12 in contrast to 113. So yeah, but the story here is not complete before you do the worst case, because this is the worst you can do, right? Because then this routine that I have then has to count to 9. about 30. So, but anyway, the slowest is 30, but it's still far away from 113. So yeah, so give me any suggestions you have. It would be really cool to make this divide by 10 faster. I can understand that the compiler uses div 8 by 8, but we are only dividing by 10, so maybe there's some special technique for 10 alone. So, or maybe I'm doing it right already up here. So finally, let's ignore this part here, and now let's start the counter. We try the slowest one first, but yeah. So there you can see. So the one you saw last time, that was with a 16 bit, so this one shall be faster. As you can see. And there. So that's much faster.